Great, thanks very much, Georgi. So yeah, as Georgi said, I'm a PhD student at the University of Cambridge. I'm not talking today about anything particularly to do with my research. Today, instead, I'm talking about how we can analyze real-world data sets to help out social scientists. In particular, I'm thinking about one data set, which comes from the UK government, who ran this survey in the summer of 2010. Your ideas for your freedom. So they were asking the public for their feedback on laws that existed, whether they thought that some of the laws should change, or whether they thought some should just be completely abolished. This resulted in one piece of legislation in 2012, the Protection of Freedoms Act, but not much other sort of public analysis has been done of this, and it's not the governmental analysis isn't clear. So myself and some social scientists I'm working with are interested in seeing what's in this data set. So what does this data set actually contain? What does it look like? This is an example, a real example of something that was submitted. So the title of the idea is that the carbon levy and green review is urgently required. They say, they sort of expand on this by saying that the government should urgently review these unnecessary levies and taxes on so-called carbon producers, and they go on to justify their idea. So whatever the agreement or disagreement on global warming or green issues, we need to review the costs and impacts of these hastily applied levies. There are also some tags that were made by the community on this website, so carbon, climate change legislation, and tax. In total, there are 5,000 or so of these responses, and 800 of these have been manually tagged with a few different categories. So with this, we've got some questions we want to answer. We want to think about how the public views the law. We want to sort of see if we can mine the data set, get some insights out of it, and use that to guide manual sort of evaluation, manually looking into what the data set contains to see how the public view the law. We also want to look at if there's any correlation between what was on the news and what was submitted to the survey. So if there was a thing about global warming in the news, was there a spike in environmental responses recorded sort of in the next few days after that? And we also want to analyze that bit of legislation that I mentioned at the beginning. Does that actually address what the public were talking about, or does it not? And the fourth, which is where my work comes in, is can we use NLP to help it with this? So on a basic level, it's useful to have some kind of computational processing of this data, because as I'm sure many of you are familiar with, it was very noisy. It was full of random HTML fragments. Cleaning that up by hand would have taken a very long time, so doing it automatically was very useful. But on a sort of pragmatic level as well, there's way too much data to hand tag this. Tagging 800 of these examples took long enough, and doing 5,000 would be prohibitively sort of expensive. Let alone sort of doing that for all of the news articles. There are tens of thousands of news articles that I scraped in the sort of 3 or 4 months that this survey ran for. So it's not possible at all to do this kind of analysis without natural language processing. So these are the tags, some of the tags that the manual coders, the manual taggers came up with. So there's a topic, which is, for this one, environment. So this is the main thing that the response is talking about. There's the sophistication. So that's whether the argument that is being made is sophisticated or not. So that's one of 4 levels. So it's very low, low, medium, or high. There's also a couple of binary tags. So whether or not a law is mentioned. So this response doesn't mention any laws by name. And there's also no vested interest here. So the person responding to this survey doesn't really have a very vested interest that they've made explicit on the levies and taxes. If they'd said that they maybe run some kind of, maybe they're an owner of a coal factory, a power plant or something, then they'd have a vested interest if they'd mentioned that. I'm going to talk today about how we can automatically code for the first 2. So what kind of questions does that let us answer? So for topic, that helps us with the middle 2 questions. If we can automatically classify the topic of those news articles and also of all of the responses, then we can easily look for correlation between the two. And then we can also use sort of that global high-level view of the data set without having to sort of go through all 5,000 to see if the legislation addressed the sort of main few topics that were brought up. So let's dive in. For the topics, I'm going to look at 3 approaches. So unsupervised approaches, semi-supervised approaches, and rule-based approaches. Unsupervised, I'm going to look at LDA, and then we're going to extend that in a semi-supervised way. This doesn't work all of the time, so we're going to then look at some rule-based systems to fill in the gaps. What is LDA? So LDA, as I'm sure many of you have heard of this, it's a common sort of unsupervised topic model that can pull out topics from a set of documents. So to train it, you just have a bunch of unlabeled documents, put it through LDA, and it will output a list of topics. You get to decide how many topics you want. So here there are n. And these topics aren't labeled. So we don't get a name or anything for these topics. We just get a list of words. So the first one, school, education, teacher, children. We can kind of guess that that's about children, education, even though we're not explicitly told. The second one, something to do with speeding. The third one is something to do with government. The fourth one doesn't mean anything. It's incoherent. That's one of the problems with LDA, is that the topics that are spat out, you have no guarantee that it actually means anything to humans. The model might have picked out some kind of correlation, but it has no means to sort of check whether that is actually meaningful. This topic is useless. If we label the document as this topic N, we wouldn't learn anything. So now that once we've trained a model, we can feed it new documents to infer what the distribution of topics is for a single document. So for this document, the speed limit should be increased to 80 mph. We use that list of topics that we learned before to get a probability distribution over those same topics. And we can see here that the one with the highest probability is topic 2, which was our speeding topic. And note that this is a probability distribution, so it all adds to 1. I'm going to briefly run through, without going into any maths, how LDA works. It's a lot more complicated than I have sort of made clear here, but that's not important, and I'm not even clear on how a lot of that works. But it's important for when we're extending it in the semi-supervised approach. The whole idea behind LDA is that we say that documents are generated by topics. So any of those documents at the bottom are a combination of one or more of those topics in the middle, and those topics in the middle, in turn, are defined, like we said before, by some list of words. So I've just I've put lines there just for the first 2 topics to what words sort of are in that topic, and this is just the initialization, so it's completely random. Both the topic word association and the document topic associations are completely random. And in the course of training, what we want to do is 2 things. We want to get a set of topics that maximally describes the documents. So we want, if we generated from the topics, we wanted to generate as much as possible of each of the different documents from those topics. And for that, we need to have good definitions of the topic. So the words associated with the topics need to actually correspond to something in the data. So we optimize these 2 things separately, and we do it iteratively. So the first thing we do is change the topic word distributions. So here the model's just decided, based on the data, to change which word corresponds to which topic. Now that we've done that, we can reevaluate which topics most generate each of the documents. So now, for example, topic 1 has changed from, or rather, let's talk about it in a document-centric way. So that first document on the left there used to be generated by topics 1 and 2. Now it's generated by topic 3. Now the model thinks that the words within topic 3 most accurately and most fully, I should say, cover the contents of that first document. Reiterate a few times until we're finished. So this is our finished setup. We have topic 1 corresponds to education. We can see that the topic, the word lists, is teacher and children, and the second topic is speed and MPH. And from that, we can see that that first document is sort of most fully described by our education topic, and the second two are described by those other two topics, that third one including the speeding one. So there are some pros and cons to this. A nice pro is that we can obtain multiple topics per document. So if you think back to that first example we gave, this is kind of mostly around the environment, but it's also about tax. So it's ideal if we can say, it corresponds to both. And even though we have the probabilities distribution, if we can assign as close to sort of 50-50 and then the rest of the topics, 0 probability, that's ideal. But the sort of downfall with this approach is that we have all of this labeled data and we're just not using it. It seems like a bit of a waste to have gone through all of that effort of labeling the data to then just chuck a unsupervised model at it. There's also the problem that some of the topics that we're interested in from the data, having sort of looked through it by hand, looked through those 800, are too similar to automatically pull apart. So you can imagine that driving, speeding, and vehicles have quite a lot of overlap in words. So probably a lot of them are talking about cars or roads, but driving is sort of distinguished by things like driver, speeding by speed camera or miles an hour, and vehicles by car, van, whatever. And it's just not able to pull that apart. So how can we solve that? What if we gave the model a hint for what words belong to what topic? And we can. So this is work by Jogalamundi and colleagues called seeded LDA. And it lets us give our own list of words per topic. So 2 questions: how, and how do we make those lists? It's a bit of a pain to make those lists by hand for all of our 50 topics, and we have all of this pre-labeled data. So ideally we can just magic these lists out of those and use them. So the answer to the second question is yes, we can. And the first one is seeded LDA, this approach. So this is why I walked through the training procedure for LDA, because seeded LDA amends this in 2 quite clever ways that let us define what we want each topic to be. So we can see a similar setup to previously. I've got rid of the other 2 topics just for clarity, but they still exist and you can still have as many topics as you want. But you can see that in addition here, we've got 2 clouds of words. And I should mention as well that these words, it's not necessarily just words that we're using. It can also be bigrams, so speed camera or miles per hour zone. Those words in bubbles are seed words. So for topic 1, we kind of think that exam and student probably relate to it. And for topic 2, those 2 bigrams, we want our topic to sort of correspond loosely to those. Now, it's not necessarily the case that our topics will end up reflecting those seed words. The model can decide if it has enough evidence to just abandon them. But it's quite a strong bias to begin with. So as before, we start with our topics consisting of just a random assortment of words. So our topic that we want eventually to mean something to do with education has event and jewelry, but we also point it towards student as well. And the effect of this is that because of the bias of those seed words, the model is biased towards picking out other words that correspond to this topic. So for example, for topic 2, we pick out MPH and speed from our 2 seed bigrams, which is great. And it solves our problem with driving, speeding, and vehicles. So, driving is motorways, drivers, traffic, speeding is speed cameras, vehicles or buses or whatever. So that's super helpful. So that's the first way in which the training procedure is changed. So that's on the word topic level. It also amends the document topic level just by sort of biasing, so it encourages documents towards certain topics based on the terms that they have. So instead of having just that totally random sort of assignment of documents to topics, we can bias it towards, so if that first document on the left contains speed camera, we'll bias it towards topic 2. It's just another way of using the supervised information that we have. Okay, that's seeded LDA. That's cool, that works. And we can just feed it with whatever list we want, and it'll do its thing. How about making those lists automatically? Well, we have these 800 document topic pairs. And what we want to do is find the bigrams and unigrams and bigrams that are most discriminatory for that topic. So if a word is sort of only really likely to appear in responses that talk about speeding, then we want to identify those and use those as our seed list. So briefly how this works is that across all of the speeding documents, we collect a bag of words. So we chuck away the word order because we kind of imagined that that's not useful. Instead, we're sort of mostly interested in mostly nouns, sometimes verbs, that sort of end up being very discriminatory, and we don't need the word order for that. So for each topic, we end up with a single bag of words, and then we use information gain to find which word is most discriminatory for each class. So we do that across all of the different classes. So here, HC is just the entropy of the class, and H of C given W is the conditional entropy of the class given the word. So you can imagine that if the conditional entropy is a lot lower than the normal entropy, then the word gives us a lot of information because it reduces the entropy of that class. So the information gain is high. That's why on the right, we take the argmax across the information gain of those speeding, comma W. And we can do that. We can not just take the argmax, we can sort of do an argsort and take the top 10. It's as simple as that. It does require some hand crafting though. So this is what was taken out of the taxation tagged examples. So you can see that that first term is not salient, possibly insane. It doesn't have anything to do with taxation, yet this technique is picked out as very salient for taxation. That's probably because it was only mentioned a couple of times in the data set. I did some thresholding, so very infrequent words and phrases are not included in this. But it's possible, if we think back to how the data originated, this is a public forum. So it's possible that someone went through and, thinks very poorly of ideas to do with taxation, so tag them all as possibly insane. There's also things like motoring regulation, so you can imagine that people are thinking about their car tax, or monarchy, that people don't like their taxes paying for the monarchy. Things like that. So it does require some sort of manual cleaning to do. And you want this to be very close to the topic at hand. So property, again, is not salient. Benefits is, I guess, closer than property or monarchy, maybe to taxation, but it's definitely not salient enough. And indeed, in our data set, it's actually its own class. So you want to be very strict with these, and especially sort of you have those information gain figures, so you can threshold on them. I used a value of sort of 3.5. Just empirically, that seemed to work well. So that's our semi-supervised LDA approach. It's great. We can control the topics that it outputs. As I mentioned before, with the driving and speeding and stuff. But even if we see topics, we can still get junk topics out. So we can get an incoherent list of words like we saw right at the beginning with unsupervised LDA. So that's things like national service and tail docking, where actually there's not so many keywords that talk about those particular issues. And sort of in those cases, the model just isn't able to pick out anything. It's looking for more than one sort of phrase. So it doesn't work. So that's where the rule-based approach comes in. So if we have these examples, I think that tail docking should be banned, or we should bring back national service. If we see tail docking or national service in a response, we can be pretty confident that that response is actually about that topic. Tail docking and national service don't come up in conversation very much. So sort of on that sort of very pragmatic view and backed up by some of the data, which I'll come to in a bit, we're fairly confident in this approach. So that's looking for keywords in the just the idea and the why section. So we can do that. We can also use these user-generated tags. So if you remember that each of the topics, the community generates a bunch of tags for them. And these tags are actually a good source of data, of supervision. So things like trade union for things to do with employment, that's very salient as a feature. It's very discriminatory for employment. That's not always the case. People were very tag happy with human rights. So the legal drinking age being 18 and the challenge 25 policy where you have to have ID unless it looks like that you're over 25, that's not really to do with your human rights. So that's an erroneous tag. So we can actually use that same approach before in the information gain to look at which tags and which sort of phrases in the topics are very salient, and in the same way as before, we have to sort of manually go through it. And actually, like in the human rights case, the information gain for the human rights category, our human rights category, was very low compared to some other topics. And that motivates us why we're doing this research. You know, these tags do exist and they're useful, but they're not sufficiently precise for the kind of analysis that social scientists might want to do. And it's worth noting that I use separate word lists for this. So yeah, between tags and phrases in the idea and why section. We've got a couple of sort of desired properties for this rule-based system. We want it to be high precision. So that's kind of what I was saying before. If we have, if we classify everything that has tail docking in it as tail docking as our topic, we don't want a bunch of false positives. So things like, you know, alcohol, for example, that's mentioned in passing a lot. So if we tagged every response that had alcohol in it as to do with alcohol, that would be wrong. So we'd have a lot of false positives, so we'd have a low precision. We also don't really mind about having low recall here. We're looking for a very precise tagger. If there's false negatives, it's kind of fine. In a lot of cases, we are backed up by the topic model. So in these two cases, tail docking and national service were not. So actually, high recall there matters a lot. But in other cases, you know, the topic model is there to back us up. This is just to give us a little bit of a boost. Why don't we just, yeah, so I've mentioned this. Here's an example of where, you know, speeding tickets, education, and alcohol are mentioned in something to do with maybe policing or something. So the results. We can see there, so for the keyword classifier, we've got very low precision and very low recall across all of the topics. But actually, we only, out of the 50 topics, we only had keywords for 7. And if we restrict our analysis to just those 7 topics in our labeled data, it recalls all of them. The precision here is kind of meaningless because that's sort of the obvious reasons. All of the examples are of classes that we know. So the tag classifier, that has quite high precision as well. That's across the majority of the topics. There's a few topics where the tags, there was nothing in the tags that sort of picked them out. And we have sort of average recall. And if we use both, then we get a slight hit on the precision compared to the keyword sort of topic subset only. But we're covering more examples here, so it's kind of fine. We can obviously also combine this with our seeded LDA approach. So the seeded LDA approach doesn't perform very well by itself. That second row is repeated from the previous slide. And together we can see that we get decent precision, average recall, and F1. It performs very similarly to our baseline. So the baseline is a calibrated SVM. It's just an SVM over TF-IDF features. So those TF-IDF features, you can imagine, is for each document, you have a list of features per word. So TF-IDF is high if a word is mentioned frequently in a document compared with its overall frequency. So speeding, if speeding is mentioned in a document like a lot compared to how much it is on average mentioned, the response is probably about speeding. But things like I, and, or, but, those have very low TF-IDF values because they're just used everywhere. So actually, you can imagine that this approach this baseline approach is very similar in its ways to the seeded LDA approach. It works on kind of picking out anomalous words which are highly indicative of a topic. And it just does that in a kind of different way to seeded LDA. There's a couple of reasons why I'm advocating for the seeded LDA and rule-based approach. So in practice, it gives better results where a response has multiple classes. So calibrated SVMs, or SVMs in general, seem to only sort of classify, in my experience, just the primary topic or just one of the topics. Whereas seeded LDA worked better when there were two or three topics mentioned. I also did some error analysis. So seeded LDA's, that third row's errors were a little bit more sensible. So in cases where, if the response was about government, it might have tagged it as government spending. Or if it was about sentencing, it might have talked about criminal law or police powers or something. So even if it got it wrong, it was kind of close. And that was less of the case with the SVM approach. It's also quite nice because we can sort of have some fine-grained control over this in a way that we can't with the SVM. So if we want to see what happens if we just remove one of the words as a feature, we can do that, and it's very quick to rerun the model. We can also add new topics if we want to. So if sort of just by looking at the data, there's a topic that hasn't been coded for in the initial 800, but actually we decide we'd like to, we don't have to code up a bunch of examples. We can just look for some salient words. We can't use the approach that I talked about with information gain, but we can just do it by hand, and it's very easy to introduce new topics. So that's topic modeling. That helps us tag all of those news articles automatically without having to do it by hand, and also helps us sort of pick out what are the main topics that people are talking about, and then we can just compare that with what the legislation actually is about. Sophistication, on the other hand, is going to help us think about how the public view the law. So if they're making arguments that are very sophisticated, that are based on the law, that helps us sort of answer the question about how they view the law. But if a lot of the responses don't, then that also tells us something. So what I'm presenting here is preliminary work. I don't have any results. It's sort of ongoing, but I'd like to just sort of touch on this. It's a more difficult task. So with topic modeling, you can kind of say, like, look, we've got all of these words. If you're talking about speeding, you're talking about, you're not talking about anything else. You're talking about speeding. But what is sophistication in a response? That's an open question. So there are some features that we can sort of come up with intuitively here. So if they refer to any laws, then it might be a more sophisticated approach if they're making arguments by being like, look at section 3C of the regulations for London. I think it's excessive. But if you just say, fines should be increased, that's less of a sort of built-up argument. And if you can remember at the beginning, we talked about how those 800 responses were coded for whether the response includes a law or not. And it's very easy to extend that by scraping all of the UK law, which is all online, and coming up with some quite complicated regexes to pick up all kinds of variations for how they might be mentioned without the year, without some of the bracketed regulations for London brackets environment or something. It's rare, I think, that people refer to the full text of the law. but we can use that as a feature, and we can use techniques from another field of NLP called argument mining to look at any assertions to pick out, this span of text is an assertion, and then look for other spans of text to say, like, this is where the assertion is backed up with facts. This is a very difficult sort of task in itself, and it's out of scope for this work. But there's some off-the-shelf software that we can use to pull out any arguments that are made. We can also use black box models, so we can just train this end-to-end using a neural network. So there's one that's very popular in the natural language processing community at the moment called BERT, which is just a large pre-trained language model that you can just train in a normal supervised way using our collection of 800 documents with the associated sophistication scores to see where we get what we get. At the moment, accuracy is around 60%, but it's early days, and sort of one interesting approach for this might be, instead of looking at sophistication as a sort of categorical class, it's not very sophisticated, it's kind of not sophisticated, it's medium sophisticated, or it's high sophistication. Maybe we can talk about sophistication on a continuous scale from 0 to 1, and that might make the task a little bit easier. Yeah, so some key takeaways. We can effectively replace manual annotation with semi-supervised topic modeling. And it's not a waste to have previously annotated data if we're going to use this approach. We can use that annotated data to speed up the semi-supervised topic modeling. And this also opens a lot of new areas for social science research. So it wouldn't be possible to look at to analyze sort of news data in comparison to what we're looking at, these survey responses without some NLP techniques. Because while the newspapers have tagged up their own sort of articles themselves, the tags, it's a different tag schema. Some of the tags are very high level. It might just be that you're talking about sports or driving or something, rather than the sort of more fine-grained things we're interested in here for our analysis. So employing NLP techniques sort of allows for this. That's me. Thanks for listening. And I'm happy to answer any questions.
All right. Thank you for your talk. It was very interesting. So if anyone has a question, please type it into the YouTube chat box or in Slido. I have one question first. You showed that in the NLP bit of the analysis, there are some differences in how people express their opinion. I mean, one could be very substantiated with facts, with proper reasoning. The other could be just like an opinion piece. Do you have any sort of analysis of how good of an argument they make, or how do you evaluate how good an argument they're making?
So this is difficult and sort of out of scope. I think it's you can look at maybe if you can look at the ratio of arguments made to sort of backing statements made. So if they make a lot of arguments, make a lot of assertions without backing it up in any way, you can imagine that that's a less sophisticated response compared with if they had made a bunch of arguments but also backed up each of them. So you can use that, but this is an entire sort of area of NLP by itself, which I think is still sort of very up and coming, and there's a lot of work to do in it. As I say, we're just using there's off-the-shelf APIs that are all open source and stuff, which is really helpful and sort of I think speaks to if you stick everything open source, it benefits everyone. But yeah, as I say, so just using that off-the-shelf software.